My name is Mark Simons. I am a professor of geophysics at Caltech in the seismological laboratory. Well, interestingly, I started off in planetary science, and I was working on data for Venus from the Magellan mission that went into orbit during my PhD. And most of my PhD concerned looking at the gravity field of other planets, especially Venus, and then developing techniques that turned out to be useful to look at the Earth. And so we started to use the same techniques to look at post-glacial rebound on the Earth, which is a topic which is near and dear to a lot of geodesists' hearts as well. I call myself a geodesist when it's convenient. I call myself a geophysicist when it's convenient. Perhaps you could say I'm an observational Earth mechanician. So I am interested in how the Earth deforms, the physical processes, the mechanics, the material properties, what it tells us about the evolution of the Earth. So we're interested in this from a physics perspective, but we need to measure it and we need to observe it. And the space of models that we can come up with is very large, and so really I view much of our obligation or our efforts is to try to restrict the space of models, to be able to reject models in some sense with the right kinds of observations. Now, of course, geodesy is a science in itself. It's a metrology. It's a study of measuring things. And there's a lot of science to be done just in how do we measure things better. How do we understand what it is we measure when we go out with a radar, a laser, or a GPS, or whatever. And so sometimes you spend a lot of effort trying to do the geodetic science, and sometimes it's more the Earth mechanics, and it just depends on the day of the week. Well, after using gravity fields that were constructed by other people at NASA's national labs, when I started my postdoc, I got interested in doing radar interferometry and GPS. So I was fortunate to have a bunch of willing advisors at JPL and at Caltech who were willing to take somebody who was going to start from scratch and do something completely different. And so that's when I started to do interferometry for crustal deformation purposes. Wow, so geodesy is one of those fascinating sciences that you go in there to try to answer one question, and then you do sometimes do that, but in the process you see something else you didn't expect. And so it gives you an opportunity to think about another problem that you didn't plan on it. So serendipity is a wonderful part of observational science. And we have gone into, well, I have typically gone into using geodetic observations to look at fault problems, fault mechanics, understand which parts of faults are creeping, which parts are stuck from future earthquakes, what happened during an earthquake, what happens with volcanoes, and so on. But then more recently, we've been interested in using these same kinds of observations to say things about the evolution of aquifers in arid environments. I come from Southern California. That's an important question. We're very interested in looking at glaciers now because in the end, glaciology and crustal deformation have a lot in common in terms of the kinds of questions they're asking and the kinds of observations that can be brought to bear and the kinds of models that can be used. So given the importance of understanding the evolution of the cryosphere, for me that's been my most recent excursion into a new field, is to look at that. We were also recently really excited that we could start to use GPS to try to say something about Earth structure, the deeper interior, or the density structure and the elastic structure of the planet. That's a completely new field that I think is going to take off. And then finally, from a really a societal perspective, there are so many things that we know we can do using geodesy that can help people in a very real way very quickly after natural disasters. We've spent a lot of time recently trying to figure out how to best exploit GPS, INSAR, optical data to help prepare for, assess, and recover from large natural disasters, earthquakes, volcanoes, and floods. And that's a very different exercise, because it may not be always the most interesting in terms of geophysical science, but it's something that we really are obligated to do because we can. For me, part of what UNAVCO does is it makes large data sets available to a large number of people. And geodetic data in particular is a kind of data set, especially GPS data, that only gets better the more data you have to process, to integrate to better geodetic science as well as better geophysical science. So all the progress that's been made in terms of understanding tectonic plate motions at instantaneous or annual levels as opposed to geologic timescales, I think has really been revolutionized 20 years ago by, I'm guessing at the age time now, by this ability. I think the ability to relatively easily go in the field as a geophysicist or as a theoretical geodesist and have somebody hold your hand and do all the hard sweat and work and help us explore the planet has been essential. And UNAVCO is a service agency in that respect, and it's been remarkable. And it means that people can come up with all sorts of crazy important ideas, and they would have never had the guts to go actually do the instrumental deployment, and now they can. So in that respect, that's something very unique in our science that UNAVCO does. More recently, with the advent of radar data, the move of WinSAR to UNAVCO and how UNAVCO has embraced WinSAR has been very important in expanding the community of people who are capable of using radar data and who are interested and are going to develop it and bring it to its full potential in the years to come. As we're facing this remarkable explosion of observations starting next month, it becomes ever more important to bring more eyes onto the data. And that only happens by having data available to lots of people easily in a way that's not so opaque, and then to have people trained. And at the same time as giving data to people, UNAVCO also supports all these workshops to teach people how to use the software to take advantage of these observations. And so it's an essential role in that respect. Well, I've only been a practicing geodesist for 20, so, and not even 20, I think, maybe 15. So I don't have necessarily the great perspective on that. Clearly, the advent of cheaper, more mobile, more robust, lower power consuming GPS receivers has changed our science. And again, UNAVCO has the role to play in making those available to all of us in an easy and a transparent way. The development of radar interferometry starting in the early 90s is probably going to be much bigger than people even recognize now, because again, as we go from sporadic measurements on monthly to seasonal timescales for a given location, and now moving towards weekly and then within 5 years daily observations from space, we are going to see things that nobody has imagined possible, right? So we are now experiencing the revolution. Geodesy is an observation. It's a data type. It provides data. And the big revolution beyond new technical revolutions in terms of radar satellites, LiDAR observations, high frequency GPS, some of the obvious things. I think, in fact, the biggest revolution is going to be what the geophysicists do with these observations. And it's going to be our ability to think very deeply about the errors in these observations and how to ingest them rigorously, robustly into models which are ever more complicated, and how we can express what we know and what we don't know. We learned, unfortunately, with the Tohoku earthquake in 2011, that we were a little complacent in thinking that the models that we had which fit the data suggested that there was no major risk for such a large event. And we discovered it's really our methodologies that were wrong. Our methodologies were letting us be too comfortable with one or two models and not realizing we had to explore much larger spaces of possibilities. And codifying that, making it rigorous, it's expensive, it's computationally expensive, and then merging or integrating that with this explosion of observations is a huge computational problem. It's a huge educational problem because it means codes get more sophisticated. Students need to learn how to do the codes. You need to do how the modeling, you need to do the observations. It becomes too much for one person. And so I think the science that we're going to do, the big revolution, is going to be how we actually deal with this onslaught of observations in order to address the critical questions that people are asking, whether it be, increasing populations and in their exposure to natural hazards, or climate change and the impact of decomposing ice caps. These are all issues which we will have to struggle together with these, with figuring out how to integrate all these large observations with these complicated tools. Despite appearances to the contrary, I still feel myself to be one of the young ones in geodesy. And UNAVCO has provided an environment that is so welcoming to its junior scientists and encourage them to go try crazy things and do things. And whether it be by just making data available, or answering questions, or helping you write proposals, we can get more data, we can get better models, but in the end we need to have the people who are excited and energized to do this. And UNAVCO is one of the very successful groups to actually provide an avenue for making sure the next generation is there to take advantage of what we're doing now.